Okay, hello and welcome to my algorithms assignment for ICS for you. So for this particular assignment, what I did was, instead of updating my data structures assignment, what I did was I essentially created an add-on for the program that was in that assignment. And so basically in my data structures assignment, it was like an ATM system where users could deposit money, create accounts, deposit money to their checking, savings, withdraw, borrow credit, etc. And then it will like calculate all that and then upload it to a database.json file. And basically for the algorithms assignment, what I decided to do was to create what would be essentially the admin view of that same database. Oh, and one more thing I think I should mention is how I generated the specific database, because I can't just go online and download, say, a database of like users or something, right? Because this is custom tailored to my specific ATM program. So what I did was I made like a separate Python script, and essentially what this script did was it just created the 25,000 users for me, and then also generated another JSON file with 32,000 users, and that's for the empirical data collection that I'll go into in a bit. But for the actual program, this generated the file database.json file with 25,000 users. And then within the actual database, you can see here, because of the method that I used to generate it, basically all of the values are completely unsorted and literally like the mathematical definition of being random. Okay, so now I'm just quickly going to walk through the like core user flow of the program. So the first thing someone would do when they, like an admin would do when they hop onto the admin side for this specific program, is of course to verify your credentials. So like for our purposes, the password is 123. So let's just see quickly what happens if I type something wrong. You can see login failed, right? So if I have the right password, it verifies me and then moves me along on the user flow. So here I can for my specific program, you can sort the users, you can edit the users, and you can create new users. And that's pretty much like all you would really need from like an admin view kind of thing, right? To sort the users by like largest account to see, like, for example, who owes the most money to this specific bank, or if you want to just manually go and edit like a user or something like that. Okay. So let's just see how the sorting works. Okay, so let's see what happens when we, for example, want to sort for some users. So if I type 1 here, my program is really like in depth in the sense that you can for each object which has the different attributes, you're actually able to sort by every single one. Let's just quickly try this out. So for example, I want to sort users by total account balance, right? Okay, so we just type 2, and because we are using the selection sort algorithm and because we have 25,000 objects, it's going to take a while to process. Okay, so it has finished processing, and we can see here that it printed out the lowest 20 accounts. So it sorts by the lowest account balances within the database, as well as the largest accounts in ascending order. So we can see here that the largest account here is at $2 million. Okay, so now let's say I want to sort the users by username, right? So let's just type 1, and then it will sort by the username based on the ASCII index, I guess is that what you call it. Okay, so our data has finished processing. It does take like, I think like 2 minutes or so, and it is quite a long time, but later on we'll see when we do the empirical data analysis that it actually is correct for how long it should be taking. Okay, so in terms of the usernames, we can also tell that it is sorted. So we can see here that's sorted with the top 20 names and then the very bottom 20 names for the lowest bound, right? So I manually created this user called Zesting123, and since the first character is first of all a lowercase, which is behind all of the uppercase letters, and it's Z, which is the very last lowercase letter. Basically, Zesting King should be and is correctly set as or sorted as the very last value. Okay, so that's kind of like the sorting, and then you could also sort by checking, savings, or credit. but just for the sake of time, like I won't go over that, but it's basically the exact same thing as the total, but with those account values instead. So now I'm going to quickly show the editing user function. So if I type 2, basically it lets me choose who I want to edit for like the user. So there's like a specific user I want to edit the details for. So just for this example, let's just say I want to change the username of Alex1 here. So if I want to change the username of Alex1, I just type the username, and then if it exists, it'll prompt me to change the details. So let's say new name is alexl123@gmail.com, and we can say the new username is alex2. So now to verify that the editing works, basically all we have to do is just search up alex1 here, and we can see here that the user no longer exists, and that's because we changed the username to alex2, right? So then now if we want to search for alex2, we can see it then allows us to edit it once again. So that's how we know that it has correctly chosen the user and edited their details. And then one more user flow you can do is to create brand new users. So you can say like alex12345 here, and wait, this username already exists. Oh yeah, and that's because it does already exist. So this creating users function does check if an existing username is already taken, just so that there's no duplicates, right? Now let's just try one that we know doesn't exist. So we know that Alex, let's say 656 doesn't exist. So now we just do name, SL, etc. Enter your name, email, username, and that's it. So now it basically just creates a new user. And yeah, that's pretty much like all of the core like user functions that you can do for my specific program, and every single one takes advantage of some aspect of the algorithms assignment, whether it's sorting or by searching. Okay, so for how my specific sorting algorithm works with my objects is essentially I'm using an insertion sort algorithm here. So what happens is my algorithm is able to sort by the username, so like by strings. It's also able to sort all of the attributes, so like the account totals, the checking account, savings account, etc. And what really allowed me to make my program like vast in the sense that I'm able to sort by every single attribute is how I kind of formatted the insertion sort algorithm for my specific purposes. Looking at this insertion sort function, it does look a bit different than like what your typical insertion sort function would look like, and that's because I have this compare lambda function that I'm also passing into the insertion sort function. And by doing this, so first I should probably talk about what it does. So basically the lambda function is like an anonymous function where it essentially allows me to pass in a function as a parameter within this algorithm. And so basically you just declare the lambda function, this function takes in the parameters a and b, and then it does the comparison of the a attribute and then the variable b's attribute. So like for this purposes, we can see here that when it does the compare, basically it'll pass in array at index j-1 as a, and then the key as b, which is array at index I. And essentially by doing this, it allows me to be able to sort my objects based on their attributes. And that's because if I was to not use the dot savings or like dot checkings, it would only compare the objects, and you cannot compare account objects with one another, right? So by doing this specifically, and by doing it with the lambda function, I'm able to really scale up this program. An effective way I could set up my specific algorithm is I could just, in this section here, in the actual function, do whatever attribute I want to compare. But because I want to sort by like 4 or 5 different attributes, I would have to then create a separate insertion sort function for each parameter that I'm sorting by. By taking in this compare lambda function, I'm able to compare whichever attribute I want, and it really helps with the scalability, because by setting it up like this, when I'm calling the function, that's when I'm defining which attribute I want to compare by. So that essentially allows me to create like an infinite amount of comparisons with however many attributes that I want, and that really helps with the scalability of the program and allows me to work with objects and compare by any attribute. So in my user flow walkthrough, I showed what the array looked like after it was sorted, and here is just a picture comparing the array before it was sorted and then after it was sorted for both the first 20 and then the last 20 items. So in terms of the computational complexity, so looking at this function, we can see that it iterates through the entire array for the first loop, and then the second loop in its worst case. So that's when an item in the array that should be at the very front is at the very last index. In that case, so like in the worst case, we see here, basically it will also iterate through essentially the entire array. So if it iterates through the entire array essentially twice within the nested loop, basically you can roughly deduce that it will have a computational complexity of O(n) squared, because operations you have to do will be n times like n-1, n-2, n-3, etc. But if you multiply out that model, it'll always come out with an n squared. So roughly you can deduce the worst case scenario just visually looking at specific programs. And then based on my research from credible sources, we do know for a fact that a proper insertion sort algorithm does have a theoretical computational complexity of O(n) squared. So in terms of which algorithm is faster, so we see here I also created a selection sort just to like test around, and basically what I found was that the insertion sort for my specific purposes is faster. Okay, so to talk about the reason why insertion sort is faster for my purposes, I think I should first talk about how each algorithm works. So for insertion sort, basically what happens is the inner loop here, it iterates through the elements that have already been sorted, and in this video I'll have like visual representations. The key thing is that the sorted elements are the ones that are being shifted over until it's been sorted. And then for selection sort, the inner loop here is the one that goes over the unsorted elements as opposed to the sorted elements in insertion sort. And in this case, basically every time it passes through the unsorted array, it'll take the lowest value and then push that to the sorted array. Basically, because of the way they are sorted, insertion sort, it moves one item each time towards its final resting places, and because of that, it will always have a computational complexity of O(n) squared. Whereas for insertion sort, only the worst case will have a complexity of O(n) squared. So essentially, insertion sort is faster for my specific program because I have such a large database that is completely random. So the best use case of insertion sort as opposed over selection sort is when you have a large array that has completely random data like me. So in that case, if it's completely random, insertion sort will usually not always have the worst case of O(n) squared complexity, and that's because the probability of having the last element or like the last few elements at the very back is quite low. Selection sort works best when you have like an already like somewhat sorted array and you just need to check over a couple or just shift over a couple of items, and that's when the best use case for selection sort is. Or if you have a backwards array that's sorted in the opposite direction of what an insertion sort would be, because that would be the worst case for insertion sort, and in that case selection sort would be better. Okay, so in terms of searching for my program, I use both linear search and binary search. So for how my binary search algorithm works with my particular objects, basically for the two searches, this time I didn't pass in any custom functions, and that's because for the searching, the only like logical or like reasonable like use case would be first if the admin side to be searching for users, and because of course it wouldn't make any sense for like a bank admin to be searching the exact balance to be able to find like a certain account. Instead, all of my search algorithms are only there for the sake of searching through the user attribute, and as a result, for the actual comparisons, as we see here, it interacts with the object by calling the .user instead of just like an open compare function like the previous sorting functions. And in my case, I'm only using binary search once, and there's a certain case that's only if the user has already sorted the data by usernames, and if that's the case, then my program calls the binary search. Otherwise, it always uses the linear search. So for my specific program and the like sorting function that I'm using, essentially there's actually like no case in which it would be worth it to use my insertion sort and then a binary search only for the purpose of searching, because the time complexity is just such a big difference that the actual complexity of binary search or linear search is negligible compared to the time complexity of my insertion sort algorithm, which is O(n) squared. However, outside of this program, normally instead of insertion sort, there's things like quicksort, which is usually what programmers use, and these sorting algorithms run in n log n time. If you use that kind of sorting, there would be a compelling case in which you would want to use a dot sort and a binary search. First of all, just looking at my program, we can see here that I'm only calling the binary search if the if the usernames have been sorted previously by the user for whatever purposes they had before. And if that's the case, then we'll just call binary search. Otherwise, all of the other instances in which we use linear search, and that is mainly because, again, for my search sorting purposes, there is simply no use case in which it is worth it to perform a sort and binary search. So basically, the use case for binary search, so we're now speaking like theoretically outside of my program, but there is a really huge actually use case for when you would want to use a sort and then binary search, and that's when you want to be calling a search function many times throughout a program. So we're talking like 10 times, like 20 times throughout the program, where you're going to be searching through a specific list. In that case, it would be worth it to perform a n log n sort in addition to a binary search, and that's because the time complexity that you save with binary search compounds exponentially the more you call it in comparison to linear search. If you think about it, like linear search, it would be, say, like a constant graph for like the amount of time every time you call the search, whereas for the binary search, it has like a steeper initial time complexity cost, but the more you use it, the more time you end up saving. So you can kind of think of it as like a high quality like tool where the initial cost will be much higher, but with more and more use in comparison to buying, say, like a really cheap tool, it'll ultimately pay off in the long run. So in terms of the computational complexity, if we go here, so linear search, as the name entails, it has a constant computational complexity of O(n), and binary search has a computational complexity of O log n. To our visual method, if we look at the linear search, we can see that it has a single for loop, which iterates through the entire array once, and then if this exists, it'll then return the index in which it found the item. And so because there's one for loop and it goes through the entire array, we can say that it does n operations. And just from that, you can roughly deduce already, visually speaking, that linear search has a theoretical computational complexity of O(n). And then for binary search, essentially, if you look at it here, this is a recursive binary search. And what happens is every single time in which binary search is called again and again, it recursively shrinks the size that you're searching through by 1/2. And in that case, it's kind of like you're dividing the searching amount in half every single time. And then if you do the log base 2 of a certain n value, you'll notice that it is roughly like half each time as well. Roughly, visually speaking, you can also deduce that because it is recursive and it's dividing the amount of searching by 2 every single time, that the computational complexity would be O log n. And then based on reputatable sources and research, we do know for a fact that binary search, when implemented correctly, even recursive or iterative, it doesn't really matter, does have a computational complexity of O log n. And through research, we know that linear search does have a theoretical computational complexity of O(n). So again, in terms of which one is faster, theoretically, if we binary search is about like half the time of linear search, except of course it comes with the caveat that your list that you're searching through must be sorted already, whereas it does not matter at all for linear search. And the reason why binary search is faster, again, it's just simple logic. It's that the binary search algorithm searches through half of the items, or like iterates through half of the amount of items as the linear search does. And again, if you're doing multiple calls of a specific search function, then it is definitely worth it to use binary search, whereas for linear search, it is actually faster if you're not calling searching and you have a unsorted array. Okay, so now on to the empirical data for the sorting and searching. So overall, this process that I use to generate the empirical data and then subsequently calculate the empirical computational complexity was quite a tedious process. And essentially, first I started off with a separate file. I used a timing function to measure the time at the start when it's called and then the end when it's finished calling. And the process essentially was I had like a table here that starts off with an input size of n of 250, and then 500, 1000, 2000, 4000, 8000, 60,000, and 32,000. From there, I just limited the size of the array based on whatever input size n I needed for this chart, and then I collected the runtime below. Now, so with just the raw data, there isn't much that you can deduce from this, because all you'll get is very strange looking exponential functions. So what you have to do is you have to, because for our input size, so this would be like our x value, we're doubling it every single time. If we apply a log base 2 to all of the values, we will then be able to deduce like a trend from it and plot a line of regression as seen on this Excel sheet. Here on this specific graph for selection sort, and also one more thing I should mention is for the empirical data, I calculated selection sort instead of the insertion sort, because for some reason the insertion sort was a bit weird, and that's of course I think because it doesn't always run at on squared, so it was giving me some weird numbers. So just for the sake of this data collection, I used the selection sort to map out the data. So the process after plotting the logarithmic scale of this input size is you then find the line of regression and then find the specific slope of that line. And then basically I applied this specific formula and then apply the log base 2, so then it looks like this specific formula. So then if we have the slope and the other value, we can then place it into this equation here, and that gives us t of n equals 2 to the power of negative 23.39 multiplied by n to the power of 2.05. And using this model, we can then note that the complexity, empirically speaking, from our data observance is that our program for the selection sort runs at a computational complexity of O of n to the power of 2.05, which is essentially these very, very similar to the theoretical computational complexity of O(n) squared. And here for the binary search, we can't apply the same equation that we just did for anything that has a base that's not n. So we know for a fact that binary search doesn't have a variable of base n, it's log n. And in that case, we can't really use the equation, and instead, so the way we can deduce that it's similar to the theoretical complexity of binary search is if we just plot just like usual, apply the exact same method here, note down the runtime, and we can see the huge difference in binary search of log n versus this one, which is O(n) squared. So essentially we plotted the exact same thing, applied the log base 2 to all of these, and then so basically what I did here was then I took a level of x values that would be like mathematical in the sense that of just raw mathematical data where it increases by 2 every single time, and then the y value would then be the log base 2 of the specific number. So we can see here that log base 2 of 4 is 2, log base 2 of 8 is 3, and then after that then apply the an additional log base 2 on the x and y values so that it is on like the same scale as our empirical data here. And then the best way I thought was to just compare the two graphs. So here we can see just roughly the slope of the empirical data plotted was 0.4 roughly, and we can see here that the mathematical plotting of on a logarithmic scale is also around 0.4, so we can roughly deduce that our binary search algorithm is correct and that it is indeed operating, has a computational complexity of log n. Finally, we have the linear search, and this applies the exact same method as our first empirical analysis. And here, same thing, it doubles the input size every single time, we collect the time, and then we plot it on a log base 2 scale. And here we see that linear search, it proves to be really true to its name. You can see here that the slope is essentially 1, and so through this analysis and the equation analysis, we can deduce that the empirical computational complexity of our linear search algorithm is n to the power of 0.997, which is very similar or pretty much the exact same as the theoretical computational complexity of O(n). And yeah, that pretty much wraps up my empirical analysis. I will be attaching this file as well to the submission.